Hey guys, welcome to lecture number 5. Today I will talk about continuity. You'll see this is another notion that we will learn. As you saw last time, we talked about limits of functions. And now today we will talk about continuity. You'll see that the limits of functions will be involved here. By the way, you see my background here? So it's not, I'm not on a bench in front of the math department. It's just a picture that I found. But anyway, this is how the math department looks like. If you, probably you know the building at some point. So if you guys want to visit me in the math department for office hours, just let me know. All right, let's get started now. Like I said, I will start with the basic notions of continuity. I hope everybody can see the screen, right? All right. Okay, so continuity is something very important for you, and you will see that this will involve not only the limits of functions, but also the values of functions. And we would like to, at a certain point, and would like to connect these two. And you'll see that continuity is the right thing to do so. So let's talk about continuity of a function at a point. So let's see, this is the definition, right? A function f is set, f is continuous at a point x equals c, right? If the following three conditions are met, and I like to look at them very, very carefully. These three conditions are the following. So the first one is that f of that point, the value of f at that particular point exists. In other words, f of c exists. This is important. The second one is that the limit of f at that point exists. So these two quantities must exist. And the third one, which is very important, and the third one will make the function to be continuous, in fact, it's not just that these two quantities, right, f of c and the limit as x approaches c of f of x exist, but they must agree. So in other words, we must have that the limit. So let me just write this in one word. So f is continuous at the point c if and if the lim as x approaches c of f of x is nothing else than just f of c. So that's what you need to know, right? Do you hear some music as well? There is some Rihanna playing outside here at the pool. No? Okay, that's good. Well, I can't hear it, so. It's not like it's bothering me, but it's okay. Since we have the smoke alarm, why not having some music as well? All right, so that's the definition. So always keep in mind that when when you will be asked to prove something about a function being continuous at a certain point, make sure you that the limit as x approaches that certain point of the function is the value of the function at that certain point. So that's what you need to do to verify. All right, so that's what it means for a function to be continuous at a single point, right? And now we will say that a function is not continuous at c. It has to, when a function is not continuous at that point, it's said to have a discontinuity at that point. In other words, we say that f is discontinuous at x equals c, right? So we say that a function that is not continuous, we say that it is discontinuous. So you have these two notions, right? So once again, this continuity means that for example, if you want to prove continuity over an entire interval, you're not going to take any point. You just take an arbitrary point from that interval or from the domain, whatever the domain is. You just take the limit as x approaches that point from the domain of f of x, and if the limit agrees with the value, then you can say it's continuous at that point. But since that point was chosen to be arbitrarily, then you can say that the function is actually continuous on the entire domain, right? So that's the philosophy. And of course, to prove that it's discontinuous, you just have to pick one point for which the limit of the function at that point does not agree with the value of the function at that point. So that's what you need to know. All right, so that's basically the definition of continuity. And now you know what continuity is at a certain point. You know what discontinuity is at a certain point. All right, so that's the definition. So keep this in mind. This will be very important. And now let's give an example. And let me just show you the graph. Look here at the graph of this function. So probably you can see what this function is. It's is the easiest parabola you can find. So it's y equals x squared. And you see that here at this, you see there's a hole here. F of 2 does not exist. Well, I shouldn't have dropped. What can you say? If f of 2 does not exist, then there is no way for this function to be continuous at the point x equals 2, right? Because the continuity at x equals 2, this will be equivalent with saying that the lim as x approaches 2 of f of x, which will be some kind of value, whatever, this will be f of 2. But f of 2, this guy does not exist. So there is no way for the limit to exist. So that's it. So this is an example that when you have a function, in this case f of x equals x squared, right? And f of 2 does not exist, so it's taken outside of the domain of the range, sorry, then there is no way for this function to be continuous. So this is just an example, right? And now let's see another example. And let me just I'm going to spoil it right from the beginning. Look at this function, right? We have seen the graph of this before. And let's see what happened at 0, right? When we take x to be very close to 0, well, 0 from the left and 0 from the right. Keep in mind that this guy here, you see, this is when I say x approaches 0 from the left, I mean that x approaches 0 for values which are less than 0. So for x less than 0. So that's what I mean by this guy here. Right, so this guy here will be nothing else than just here. That's what we mean by 0 minus. And as you can see from the picture, from the graph, you can see that the limit as x approaches 0 from the left, so 0 minus of f is negative infinity. And the same thing goes from the right. So this guy here, you see 0, this is nothing else than just x approaches 0 for values greater than 0. So that's what we mean. All right. But you see, the two limits are different. So the first one is negative infinity, the other one is positive infinity. So the limit does not exist. So therefore, since the limit does not exist, then you cannot say that the function is continuous, because continuity would imply that the limit as x approaches 0 of f of x is actually equal to the value, but even the limit, this guy does not exist. So there is no way to make this function continuous. Right? Okay. Any questions so far? Is it clear? All right. Please, like I said, feel free to interrupt me at any time. You can be vocal, you can write on the chat. I would prefer you to be a little bit vocal, but it's fine either way, because here I have to look on the chat, you know, I have to, but in any case, feel free to ask questions anytime you have one. So I'll try to go as slow as possible so that all of you will understand what's going on, but don't hesitate to interrupt me. All right. Now let's see another example of a function that is not continuous at a point. And this function here, look at the graph. You see, it's and you just look at the picture very carefully first. So if you look at the picture, you see you have a line, we have some kind of a curve there, like almost like a parabola, and it passes through the point 1, and we have the domain is cut somewhere between 0 and 1. Anyway, so, but as you can see from the graph, when x approaches 2 from the left, pay attention, when I say x approaches 2 from the left, I mean for values. Look at this guy here. So 2 is the critical, x equals 2 here is my critical number. And let me just separate these. Oops. Maybe wait just a second. You see, we can separate this 2 at the point x equals 2. Look at them. So for values less than 2, so for this part here, less than 2, something happens. And for values greater than 2, something else happens. So what happens when x approaches 2 from the left of f of x? Well, the limit, if you look at the graph, is what's happened here, right? It's this guy here, right? This guy here, right? And as you can see, it's the value as x equals 2, it will approach 4. Look at that, right? As you can see here. All right. And if you look at the graph, as x approaches 2, but from the, let me put some other color here. Okay, this one. You see, when x approaches 2, but from the right, we have something like this. And well, let's see, where does it go? It will go to somewhere at 3, right? Somewhere here. Anyway, see, somewhere is 3 here, which will correspond to this. So as you can see, those 2 points do not agree even with each other, so the limit does not even exist. If it existed, those 2 points must have agreed with each other. Right? So if the limit does not even exist, so there is no point of talking about continuity. So no point. Okay. So therefore, this function is not continuous at the point x equals 2. Right, I hope it's clear from the picture. Now let's see another example of a function that is not continuous, but this time the limit exists, is actually 4, but that is not equal to the value. Now let's look at the picture. I'm taking again a parabola. You see the limit as x approaches 2 of f of x is 4, right? It's clearly here, but we have a hole here at f of 2, which is not 4. It will avoid the value 4. See, it's a hole. So by the definition, if f was continuous at x equals 2, then the limit of f of x would have been, so this, let me write here, f is continuous at the point if the limit as x approaches 2 of f of x is the same as the value f of 2. But the limit, we know that this is 4 and f of 2 is 2. As far as I'm concerned, these two are not equal. So there is no point, there is no way to make this function continuous at the point x equals 2, right? In fact, I'll go look at this again, keep this in mind, and I'll have to go back to the definition. Look at the definition. You see what I highlighted in red? The limit as x approaches the point C, which in our case is 2, of f of x has to agree with the value at that point, which in our case is f of 2, right? If we go back, you see, there is no way these two agree, you see? The value of f of 2 does not agree with the limit of f at the point 2. All right. Now, I think you have seen a couple of examples of discontinuous functions at a point. You have seen when the limit does not even exist, so there is no point even talking about continuity. But also you have seen this example when the limit of the function actually exists, but does not agree with the value of f at that point. Now let's talk more about continuous functions. And let's just say this is very, very important. And I think this will somewhat be, will make the picture even clearer. And we say that a function is continuous if the limit equals the actual value of the function. What we have just been saying, so that's what you need to know. This is important. So a function is continuous, once again, a function is continuous if the limit equals the actual value of the function, right? As we have seen at the beginning. And now informally, let's see what this means. We can also see this graphically. When you have a graph which is not interrupted, then you have a continuous function. Right, so continuous functions can be graphed without lifting the pencil. That's what we can say. And that's what you need to know about continuity. So keep this in mind. So their graph is not interrupted, is uninterrupted. Okay. So now, having this in mind, let's talk about some continuity theorems. When do we expect to have continuity? Well, as you can imagine, common functions that are continuous at any point. So if you pick an arbitrary point x equals c, for which f of c is defined, well, you can say something like the power functions, right? X to the power something, whatever, x to the alpha, right? F of x. So these are the functions that x to the power alpha, right? Polynomial functions, which look like something like this: a n x to the n plus a n minus 1 x to the n minus 1, and so on. Rational functions, you can expect continuity here, right? right? Something like f of x is the ratio of two polynomials, p over q, with q non-zero. Trigonometric functions, you have sine, sine, cosine, tangent, cotangent, secant, cosecant. The inverse trigonometric functions such as sine inverse, cosine inverse, tangent inverse, you name it, right? Also, there will be some other two functions that we will study, and this will be called the exponential and logarithmic functions. Anyway, we'll deal with that in a future lecture. So these two. So this will be devoted for a future lecture. In fact, the next lecture will be devoted to this. If I'm not mistaken, this will be lecture number 6, right? Anyway, we'll get to explore more about exponential and logarithmic functions. And you'll see some properties and how are these functions related to the limits of functions in continuity. Anyway, so these are the examples that you should expect to find continuity. So in other words, more or less, if you don't have some restrictions to the domain, these functions will be continuous. All right. Now let's talk about some properties of continuous functions. And let's just start by saying that if f and g are continuous at a certain point, C, then the following are also continuous at that point. And let's see how does continuity behave? First of all, you see continuity behaves really well. The first property is the scalar multiple. So when you multiply any scalar, any constant s, let's say, by the function f, right? So let me just make myself clear. This is s times f of x, right? This is a constant here. So when you multiply any constant by the function f of x, this is continuous. This is continuous. Right? So always this will happen. F continuous, any scalar multiple of f will also be continuous. Now the sum, when you have the two continuous functions, f and g, then clearly the sum will be continuous, right? Also, the difference is more like a sum because the difference is nothing else than just f plus negative g. So if the sum is continuous, then the difference follows immediately. The product, the same thing. So this is f of x times g of x is also continuous. The quotient as well is continuous. So if f and g are continuous, then f over g is continuous. But pay attention, for the quotient to exist, we need to know that the function g evaluated at the point C is non-zero. So the bottom is non-zero. And not just that, not just the sum, difference, product, and quotient, but even the composition is also continuous. But provided that G is continuous at the point C and F is continuous at the point G of C, because we need to remember F composed with G of X, let's say, is nothing else than GF of G of X. So if we take the limit as X approaches C here, then we need to have some information about G of C, and also we need to make sure that F is continuous of G of C, right? And G is continuous at C, so right, the lim as X approaches C of G of X is nothing else than just G of C. So keep that in mind. We need this. Okay. So these are the basically the properties of continuous functions. They are more or less expected. I don't think there is any surprise here. You have seen so far what to expect. You have seen which functions are continuous, which functions can be continuous. Okay. Now let's talk about continuity on an interval. This will be tricky a bit. And I would like to start by saying that a function f is continuous on an open interval AB if it is continuous at each point in AB. Just like I said, not just an open interval, any domain you pick, a function is continuous at that point if it is continuous at each point in AB, right? So in each point in that domain. Okay, right, you just pick an arbitrary point, let's say C in AB, and you prove continuity at C, then since it was chosen arbitrarily in that interval AB, then the function is continuous on the entire open interval. And now let's see what happens for the closed interval. We say that a function f is continuous on a closed interval AB. As you can see, I'm also including the endpoints here, right? Is not the closed interval AB. Let me just write it here. Is nothing else than just the open interval AB reunited with the points A and B, right? The endpoints, right? So therefore, we need to discuss the endpoints. So we say that the function f is continuous on a closed interval AB if f is continuous on the open interval AB. And moreover, these two things happen. So we need to talk about the values, the limit at the endpoints. So the limit as x approaches a from the right is of f is f of a, and also the limit as x approaches b from the left of f of x will be f of b, right? Just like applying basically the definition. So they must agree at the endpoint. And now we can say that the function f is said to be continuous from the right at a and continuous from the left at b, respectively, if the above two limits hold, right? Just like we said. All right. Now, let's give an example. And in fact, I would like you to look a bit for a couple of minutes. That was a good one. You should tell him it's not the case. I hope you told him. Oh, I'll get this fixed so that. Yeah, you can make fun of him. Just don't tell him. Just like, yeah, you can keep searching about the smoke alarm in the house. But he won't be happy when you tell him the truth, though. But if you want to make fun of him, yeah, you can do that. Anyway, so let's look at this. Describe the intervals of continuity for the function g of x. The function g of x, as you can see, is given by the square root of 1 minus x squared. So this guy here is 2. You already told him, okay. So this is 2 here. So it's 1 minus x squared. That's the function. Yeah, you should get the group me chat for this class. Okay, so how should we proceed here? First of all, we would like to see this function. You see, we have to see the domain for which is defined. You see, we need to determine the domain first. So when we determine the domain, now you guys are giving all your Snapchats here. I have one too, by the way. So like I said, determine the domain. So we must have, since we deal with the square root, right? We need to make sure that the quantity inside the square root is non-negative, right? Always. So in our case, we must have something like 1 minus x squared is greater or equal than 0. Okay. And this will imply that the domain is nothing else than negative 1, 1. So the function g is defined, right? And it will be r, but let's just say it's not going to be r, it's going to be 0, infinity, something like this. So that will be the domain. Now the question is the function continuous on this domain? What do you think? I'm actually curious what's your answer. Let's think a bit. So what do you think? Is the function continuous at the domain? So what would you expect? What's your suspicion? Well, what do you think? You'll be tempted to say yes, right? I mean, why not? It's just a composition of the square root of a polynomial function. So why not should it be continuous, right, on the domain? It's natural to say, well, exactly just like we said, it is continuous on negative 1, 1, right? On the open interval, due to power function, polynomial function, and composition, right? So it's just a composition of the power function and a polynomial function. So that's what it is. Okay, but now let's see what happens at the endpoints. That will be important, you see, because we said that this is defined on a closed interval, negative 1, 1. So we need to make we need to see what happens at its endpoints. So we need to make sure that g is continuous at its endpoints. And we see the first one, that the limit as x approaches negative 1 from the right of g is 0, which is the value, g of negative 1, which is great. And also, the limit as x approaches negative 1, the limit as x approaches 1 from the left of g of x is, again, g of 1, which is 0, right? Well, if these two agree, as you can see, right? So this is, let me just write it here. So the limit as x approaches 1 from the left of g of x, and this guy is the limit as x approaches 1 from the right of g of x. As you can see, they agree with the value at, negative 1 here. Here is negative 1. Sorry, just a second. So the first one is negative 1, and the second one is 1 from the left. Okay, this is 1 here. I hope it makes sense. You can see it. Okay, so they agree with the values at negative 1 and at 1. So which is great, which makes the function continuous on the entire interval, on the entire domain of definition. right? Does this make sense? Any questions so far about this example? Is it clear for everybody? Okay, that's good. Okay, so keep this in mind. You see, you need to determine, well, what is the intervals of continuity? Well, the entire domain. So you can say that G is continuous on the entire interval, on the entire closed interval -1, 1. All right. You'll see some other examples like this, especially in your homework. By the way, I think I uploaded homework 2 and homework 3 as well. So you can see them on your web work. And I think the deadline is somewhere in March, something. Anyway, so this was a very nice example to see how you play with continuity. And you can cook up plenty of other examples of this type. All right, now let's talk about continuity of suspicious points. And you will see what I mean by this. And I'll give you an example. But first, let's see what is a suspicious point. Well, a suspicious point is a number C where either the defining rule for the function changes, for example, when we have some kind of piecewise functions involving absolute value or substitution at the point causes division by 0. So that's what we call a suspicious point. Well, unfortunately, at some point we have to be suspicious. Yeah, usually you don't have to, but you know how people like to go to the danger zone and they're always suspicious. They're always curious about things, and this is what happens. And let me just give you the standard prototype for this. You see, this is the function. Look at it. So this is a piecewise function, and so this is a piecewise function. And I'm not going to say if it's continuous or not. I would like you to answer this question. So what do you think? Do you think this function is continuous or not? So what does your intuition say? Something is odd, needs to be changed. What is odd exactly in here? So you see, first of all, what is the suspicious point? Well, it's suspicious, but what exactly is suspicious, right? Let's be clear here. What is the suspicious? You see, because, okay, let me put it this way. 1 over x. All right, it's very suspicious, but even before we even go there, what else is suspicious here? All right, let me put it this way. Do you see any suspicious point that we need to see to look at it, look better at it? What is that suspicious point in this piecewise function? 0, correct. So the suspicious point is 0. So we need to take care of 0. So let's just write this. So the suspicious point is x equals 0. So that's what we need to take care of. We need to take care of this guy. And okay, so this is a suspicious point. So, well, if this is a suspicious point, and if I would like to talk about continuity at this point, what do you think? What does your intuition say? Do you think the function will be continuous at this point or not? You'll be tempted to say maybe it's not, because it's piecewise. Even you'll see that not all piecewise functions are discontinuous. There are some of them, a bunch of them that are actually continuous. So they need to agree at that point, you see. And actually, this goes back to something that we have discussed even at the beginning of this lecture before we started recording about the Squeeze theorem. But anyway, so as we have said, this is a suspicious point because the rules are changing here. But first, what is the domain of F? Clearly, the domain of F is all the values. Somebody said that 1 over x is suspicious, so we cannot have x equals 0. Or another question we would like to answer, if, just like we said, if F is continuous. So, what do you think? Is this continuous or not? In other words, so let's just say that F is continuous at x equals 0 if what? If the limit as x approaches 0 of f of x is f of 0, which in our case, if we look at 0 here, f of 0 will be 0. So in other words, f is continuous if the limit as x approaches 0 is 0. Well, what do you think? Is the limit as x approaches 0? So let me write here. Is it true that the limit, so is it true that the limit as x approaches 0 of sine x squared times sine of 1 over x is 0? That is the question. What do you think? Is this true? Well, it is, but just like we said, it is the Squeeze theorem. Said yes by the Squeeze theorem. So how do we squeeze this? Well, if you look here, okay, where should I write? In fact, I will do it here. So look at this squeeze. So look at, in fact, I can erase here. Let me just do it. Right, by the Squeeze theorem, let's see what do we have. We have that x squared times sine of 1 over x. We know that sine of 1 over x, let's take the absolute value, is greater or equal than 0. And this is less than, since, okay, or maybe I should put, this is equal to the absolute value of x squared times the absolute value of sine of 1 over x. But sine, we know that this is bounded, is less than 1 in absolute value, so this is less or equal than x squared in absolute value. And this, as x approaches 0, will approach 0, right? And of course, this will be 0 as x approaches 0. So by the Squeeze theorem here, x will approach 0, just like we said at the beginning, right? Is it clear for everybody?
Yes, sir.
All right, that's good. If you have any questions, just let me know. So this is how we squeeze. You see, you have two functions. In our case, f is 0, no, f less than g less than h. So f is 0, h is x squared. Both of them go to 0, so g is between them, so it gets squeezed to 0 as well. All right, so in other words, now, what can we say? Is the function continuous at the point x equals 0 or not? What do you think? Is it? It is, correct? Right. So it is by the Squeeze theorem. Okay, that's good. So you see, this is an example of piecewise function. You just look at it. A classical prototype of a piecewise function. Piecewise, and let me add here something, continuous functions. All right. Okay, now let's talk about something more, a little bit more qualitative. You have seen a bunch of examples how the functions are continuous and discontinuous, and we saw some different type of discontinuity, but anyway, I'm not getting into that at this point. But now let me talk about something very important about continuity, and this is what we call the intermediate value theorem. But first, let's see what is intermediate value property. And this is very important. It will be related to continuity. So this is, in fact, the power of continuity. And it says that if f is a continuous function on a closed and bounded interval a, b, and L, and I have a number L between these two values, well, I always have to say between f and f of a and f of b, because I don't know which one is larger, f of a or f of b. Well, if you look here on this graph, f of b is larger than f of a, but anyway, that is not always the case. It can always be the other way around. So that's why we say that L, this number is between f of a and f of b, as you can see here on the y-axis. Well, if I have a continuous function on the closed interval a, b, and if I have a number L between f of a and f of b, then there exists a number c between a and b. So there exists a number c here on the x-axis, right? Which will correspond to that value L, to f of c, such that f of c will be L. This is the point of coordinates, let's say c and f of c, and will correspond to a value L between f of a and f of b. This is what we call the intermediate value property. Let me write it this way. Intermediate value property. Or we abbreviate this by IVP. So in other words, we will say that continuity, let me just write it here, continuity implies intermediate value property, but not the other way around. Okay, let me write it this way, IVP, but not the other way around. So if I want to go back from IVP to continuity, that's not true. All right? That's always the power of a function being continuous. Well, and of course, this will happen on the closed interval AB, so keep that in mind. This will be important, and you will see why this will be important, because this will give us some information about the value of maybe about some roots of a continuous function. Anyway, we'll see that immediately. And now let me just draw your attention with the following corollary. Well, a continuous function on a closed interval a, b takes on every value between f of a and f of b, right? Which is, wow. So it doesn't leave any value out. It takes every value. So keep this in mind. This is important. Takes on every value between f of a and f of b. Let me stress this again, and this will be important. In other words, if you have the interval, closed interval a, b, through continuity, f of a, the interval a, b will be a closed interval, which is important. And if you look at the graph, it basically just illustrates. You see, the graph is not interrupted. You see, it just keeps going. It goes up, down, whatever, but it's not interrupted. So that's what we mean a continuous function. And it clearly takes on every value between f of a and f of b, right? Doesn't leave any value out. That's one of the important things about how we apply the intermediate value theorem. How intermediate value theorem plays an important role here. But again, this comes from the power of continuous function on a closed interval. That's what we, all right. So keep this in mind. And now let's see some applications of the intermediate value theorem. All right, this is a very, very nice application, actually. We suppose a girl, we see some real world applications, like you would not expect this, but suppose a girl is 5 feet tall on her 30th birthday and 5.5, 5 feet 5 on her 40th birthday. Well, guess what? Then for any height h between 5 and 5.5, let's say, there must be a time t at when her height was exactly h. For any height h. Can you believe this? Well, this is an application of the intermediate value theorem. In other words, it says that if you have, let me just translate this a bit so that you can see it better. So we have a girl, right? And we have this function height. Her height is a function of t, right? Time. And this, so this is the height function. And this is t of time. Right? And we know that this function h is, somebody has his mic on, I think that's Dylan. Dylan, I think you have your mic on. Anyway. So, and this will be defined from the interval, don't worry about it. Will be defined on what interval, if you look, let's look. So it's 5 feet, between 5 feet and 5 feet, 5.5, right? Right, and well, as you can see, there must be a time t for, so for which this was exactly h, which is exactly the intermediate value property. So, okay, let me put it this way. So this is the height function. Let me just write it in words. Of variable time t. And of course, by the intermediate, since this is a continuous function, see your height will keep growing up to some point, right? But since you're between these ages, usually it's supposed to grow. Well, it's not necessarily true in any case, but at some point in your life, you'll have to grow, right? So in this case, in this girl's case, so she's between 5 and 5.5, and this will define a continuous function, this height function, right, of variable time t. So at some point, for any time, there has been a time t at which her height was exactly h. So for example, since between 5 and 5.5, there was a time for which her height was 5.4, for example. So keep that in mind, or 5.3, which is kind of obvious if you look at it, right? Of course, you cannot jump like, today I was like 5.5, 5.2, and tomorrow I'm 5.5. Well, you can jump like this, but at some point, at some time, probably in your sleep or whatever, you were 5.3 or what, something like this. So that's what you have to keep in mind. It's a continuous function, so it has to go through all, it has to take all those values. Anyway, so this is the power of the intermediate value theorem. And now let's see another power of the intermediate value theorem, and this will be related to the root location theorem. So this will tell us how to find roots of a continuous function on a closed interval. So I would like you to look at this. If f is a continuous function on a closed interval a, b, and if look at this. If f of a and f of b have opposite algebraic signs, then f of c is 0 for at least one number on the open interval a, b. Wow. In other words, a continuous function that goes from the negative to the positive has to go through 0. As you can see on the graph here, it has to go through this point here, right? For which f of c is 0. It has to cross the x-axis. Let me just write this a little bit more mathematically. So f, in fact, let me write it with a different color so that, so f defined on a closed interval a, b, and real value. This is continuous. And f of a, let's just say is less than 0, or if you want, okay, let me just put in one word. This condition that f of a and f of b have opposite algebraic signs. So this condition can be put in one word, that f of a times f of b is less than 0, right? If this is less than 0, then guess what? Then you can say that there exists some c. Okay, let me write it this way. That f of c is 0 for some c in AB, right? So that's what you need to know. We can summarize this in the following way. So that's the condition here, when you have opposite signs. This is so powerful that it will tell you the fact that f will have a root if f has opposite algebraic signs at the endpoint. So basically, you have a continuous function in the closed interval AB. You look at its endpoint. You evaluate the function at its endpoints, and if the product is less than 0, then you'll have a root, which is great. Which is absolutely great, right? Okay. Let's see an example. So this is more like a proof-based example. How would you prove this? So show that this function x squared plus x minus 6.3 has at least one root in the interval 1, 4, closed interval 1, 4. What would you do? Man, I have so much power, a power effect here that some people just went to sleep. So how would you approach this problem? So what do you need to do? Plug in what? Plug in what? So let's see, on what? Okay. So f is defined on what interval? 1, 4, right? And real value. Is this function a continuous function, first of all? Clearly, it's continuous, yes. No problem. It's just a linear combination of continuous functions. Okay, and what else do we need to do? Look above. F defined on AB is continuous, then I need to show that it has at least one root in 1, 4. What is the thing that I need to check? That f has opposite signs, right? Right, look here, f opposite algebraic signs. So in other words, we need to do what? We need to compute f of 1, which is something, and f of 4, which is something else. And if both these two values of the functions, these 2 points, right, these the value of f at 1 and 4 have opposite signs, then I can say that it has at least one root based on what I just said here. Look here. So let's see. F is, like I said, it's a polynomial, so it's continuous. And now let's look at the values of f at the points 1 and 4. So f of 1, if you plug it in, it will give you negative 4.3. And f of 4 will give you 13.7. So as you can see, one of them is negative. So this guy is negative. This other guy is positive. Right? So since the product is negative, so f of 1 times f of 4 is negative, then guess what? Based on what we said here, right? You see here, we can say that then f has must have a 0 in the open interval 1, 4 by the root location theorem. Does this make sense? This is pretty standard if you know the root location theorem, right? All right, let's see another example. So I'll just play with some examples now. The same thing goes for prove that this equation cosine of x equals 2x has a solution on the interval 0, 2. You see, now it's formulated a bit different. So how would you approach this? The way you will approach this, well, you see, this is an equation here. So this is an equation. So you have to show that has at least one solution in that interval. So you'll consider the function, let's say, f of x to be cosine of x minus 2x, right? And f will be defined on the closed interval 0 pi over 2 and real value. And of course, this will be a continuous function. So this is a continuous function. You don't have any problems since cosine is continuous, negative 2x is continuous. So you have operations with continuous functions. And now, even more, we will evaluate the function f at its endpoints. And once we do this, if you look, right, at 0 will be 1. Cosine of 0 is 1. And if f evaluated at the pi over 2 will be nothing else than just negative pi, which will be negative. So you see, one of them is negative, the other one is positive. So by the root location theorem, it will have a 0 between them, right? So it follows that f of c is 0 for some c on the open interval 0 pi over 2. That's what you need to know, right? Okay. That's another example, and probably what about if we have something like this? But you see, the difference is that I will change the interval. It's not going to be 0 pi over 2, so it will be pi over 4 pi over 2, closed interval, right? So how would you approach this? You'll do the same thing, right? So you'll consider the function f of x is cosine of x minus x cubed plus x. And the same thing goes from, it's defined on the interval pi over 4 pi over 2, closed interval, real value. Again, this is continuous. So this is continuous, right? And again, we will just evaluate the function at the values pi over 4, so at the endpoints of the interval, right? As you can see here, we evaluate f of the function f at pi over 4, and if you plug it in, and I'll leave this to you as an exercise, so to show that this is this goes back to the values of the trigonometric functions, right? And if you evaluate f at pi over 4, it will be positive, and at pi over 2 will be negative, right? Again, I'll leave this to you as an exercise. Again, by the root location theorem, there must be a 0 between these two, right? So this is basically standard at this point, so you know exactly what to do. You just need to look for the to define the right continuous function. You look to evaluate that continuous function at the endpoints on the interval or which is defined, and then you see that at one endpoint is positive, at another endpoint is negative. So by the root location theorem, it will have a 0 between those two endpoints. So what's the connection? So at the end, I want to talk about what is the connection. Well, let's explain how we have to, the connection is that the root location theorem follows from the intermediate value property. Well, how does it follow? So what does the intermediate value property theorem say? So this will imply this. Well, guess what? Look at this. So for any, let me just explain this, and I think we'll stop here. So for any lambda between f of a and f of b, there is c in the interval a, b, such that f of c is lambda. So that's the intermediate value theorem or intermediate value property. Well, the root location will follow immediately, right? Because if we define this function, let's say h of x to be f of x minus lambda, and if you evaluate h at a, right, it will be f of a minus lambda, and h of b, this will be f of b minus lambda. One of them will be positive, so this one of, in any case, we have that, so looking at these two, we will have that h of a is, or times h of b is less than 0. So it will follow that h of c, since at some point h of c is 0. So that's how the two are related. So basically, they're just equivalent, I would say, at this point. So it follows immediately for the intermediate value property, or theorem, whatever you want to call it. Right? This is how strong this intermediate value property is. So keep this in mind. And it follows, everything follows from the continuity. These are more qualitative properties of continuity. Okay, well, at this point we talked about, I think this sums up the lecture for today. In the next lecture on Wednesday, I would like to talk more about exponentials and exponential and logarithmic functions. And I think this will sum up the end of chapter 2 as well. All right, guys, I'll stop here. I'll invite you to the office hours in like 11 minutes if you have any questions. Okay, I'll see you. Bye-bye.